Hello students, in today's lecture we are going to cover Cauchy's first theorem on the limit, right? It says, statement of this theorem says that statement of this theorem says if an limit of an is L, okay, if limit of an is equal to L, then limit of a1 plus a2 plus a3 up to so on plus an divided by n is also equal to L, right? So basically limit of this number is equal to this number, right? So how it is relevant in this section of sequences, right? So it is pretty relevant here because we say an converges to L when limit of an is equal to L, right? So here also you can see if limit of an is L, then it means an converges to L, right? So an converges to L here. If an is converging to L here, this means this sequence, okay, if you call this xn, this sequence xn also converges to same L, right? So this is the statement of Cauchy's theorem on first limit, right? So firstly we are going to take some examples on this theorem, and then we will be at the end of this section, at the end of this lecture, we will be proving this, right? So firstly let us take some examples, okay, some problems based on Cauchy's theorem on limit, okay? So problem first. Problem number 1. Prove that limit n tending to infinity 1 by n 1 plus 2 raised to power 1 by 2 plus 3 raised to power 1 by 3 plus up to so on plus n raised to power 1 by n, okay, it is equal to 1. Prove that this limit is equal to 1, okay? So pretty simple, you see, pretty simple, right? You see it could be written here, this a1 is equal to 1 here, a2 is equal to 2 upon 2 raised to power 1 by 2, and a3 is this, right? And this is an, okay? So again this is becoming the same term again, right, as we saw here, okay? So we know limit when n tends to infinity, is equal to limit of n tending to infinity of n raised to power 1 by n is 1, right? So we know this. So therefore by limit of this thing is 1, therefore by Cauchy's theorem, okay, Cauchy's first theorem on the limit, you should have written it. Cauchy's first theorem on limit says that limit n tending to infinity a1 plus a2 up to so on an, okay, and here 1 by n is equal to 1, right? So therefore limit n tending to infinity 1 by n 1 plus 2 raised to power 1 by 2 up to so on, n raised to power, this is also equal to 1, right? So therefore we can easily find out the limit when we are having such situations, right? So let us try to do one more problem. Okay, problem number 2. Find out the limit, find limit n tending to infinity 1 by n 1 plus 1 by 2 square plus 1 by 3 square up to so on plus 1 by n square is it, okay, find this limit. Okay, find limit this. Okay, so here also you can see the form of the form in which we have asked to find out the limit is pretty same, okay, pretty similar to the case we have discussed earlier, that is it is in this form 1 by n an plus a2 up to so on an. Okay, so here if we know the limit of this term, then the limit of whole would be equal to the limit of the same term. So here also you can see an here is 1 by n square, right? So we know, and we know the limit, okay, right? We know the limit of this function. What is the limit of this function? Limit of this function is equal to 0. Why it is equal to 0? See, limit of n tending to infinity an is equal to limit n tending to infinity 1 by n square. Okay, so it is 0, right? So now nextly, if limit of this function, this term is 0, it means limit of, according to Cauchy's first theorem on the limit, therefore by Cauchy's first theorem on the limit, limit of n tending to infinity 1 by n 1 plus 1 by 2 square plus 1 by 3 square up to so on 1 by n square is also equal to 0. Okay, so now one last problem. Okay, after that we will be probing this result, right? So last problem, limit, find out the limit n tending to infinity 1 by n, okay, 2 by 1 plus 3 by 2 plus 4 by 3 plus 5 by 4 up to so on plus n plus 1 divided by n equal to how much? Okay, so limit of this term we are going to find out. So easily you can figure it out from here, that an is equal to n plus 1 divided by n here, and find out the limit of this function. It could be written as n by n plus 1 by n, which is equal to 1 plus 1 by n, right? So therefore limit of an is equal to limit of n tending to infinity 1 plus 1 by n. Okay, right? So therefore it is equal to 1. So see here from thus by Cauchy's first theorem on limit, we conclude, okay, we conclude that limit of n tending to infinity 1 by n, 2 by n, 2 by 1, 3 by 2 plus up to so on plus n plus 1 divided by n is equal to 1, because limit of this is 1. So therefore limit of this whole term will be also equal to 1. Okay, so these were the some problems which we solved with the help of Cauchy's first theorem on the limit. Now we are going to prove this theorem, right? So see, proof of this theorem. So firstly I'm going to write statement one more time, statement of Cauchy's first theorem on the limit. It says if limit of n tending to infinity an is equal to L, then okay, then limit of n tending to infinity of 1 by n, a1 plus a2 up to so on an is also equal to 1. Okay, so proof of the theorem, proof, right? So see, given limit of this term is equal to L. So therefore by definition of the limit, it says for epsilon greater than 0 there exists m such that difference between a n minus L is lesser than epsilon for all n greater than equal to m. Okay, so the proof I'm going to tell you right now is pretty simple proof. You will see in your book there would be also given a proof over there, but that proof is pretty difficult. So I want you to just note this down and keep the copy of this proof to with yourself, right? So that when time comes that you need this proof, okay, you can easily look at it. Okay, look at it. Okay, so now, so nextly we are going to do what? So we want to prove that, and what we want to prove, okay, so that also we are going to write it here, that also we are going to write here. Okay, we shall prove that, okay, give this equation number 1. Okay, we shall prove that limit of n tending to infinity 1 by n an plus a2 plus a3 up to so on an is also equal to L. Okay, so for that we will have to prove that difference of this term and this, right, is less than epsilon. Okay, so see, so we are going to write difference, we are going to check what is the, ये हमारा difference इन दो terms के बीच में कितना आएगा, हम we are going to check this, right? So plus 3 up to so on plus n minus L. Okay, so it is equal to, simplifying this we get a1 plus a2 plus a3 up to so on plus an minus nl. Okay, LCM ले लिया, okay, divided by n, close. Okay, so we have taken LCM, right? So now further you can write it as a1 minus one second. One second, wait for us a while. Okay, in this way we won't be able to prove this, right? So we will have to think something else. Okay, so for this you just do one thing. Okay, we shall prove this. Okay, we want to prove that this is equal to L, right? So you do what, you say let this term, इस टर्म को क्या बोल दीजिए, Tn बोल दीजिए. ओके, राइट? सो कॉल Tn इज इक्वल टू An minus L. Okay, that is An is equal to Tn plus L, right? So now this is your xn. Okay, if this is your xn, so xn is equal to a1 plus a2 up to so on plus an divided by n is equal to कितना हो जाएगा ये, t1 plus t2 up to so on plus tn plus divided by ओके, प्लस एन एल, ओके। सो क्योंकि एन टर्म है यहाँ पे और हर टर्म के साथ एल है, ओके। सो ये कितना हो जाएगा, एन एल डिवाइडेड बाय एन, ओके। बिकॉज, क्यों ऐसा हो रहा है, बिकॉज योर ए वन किसके इक्वल है, ए वन प्लस एल, और दूसरा ए टू प्लस एल, ओके, ये ए एन प्लस एल, राइट। सो in this way you will be getting nl here, okay, nl. So that's why I have written nl here. So if I write, it can be also written as t1 plus t2 up to so on plus tn divided by n plus l, ठीक है। ln को जब आप n से डिवाइड करोगे you will be having only l, right? So see, तो हमें क्या प्रूव करना पड़ेगा अब, since you know pretty simple, okay, you just keep this thing in your mind, okay. So this is your equation 2, right? Further, since as per according to equation 1, okay, since an goes to L here, okay, and Tn is equal to An minus L. So this implies limit of n tending to infinity Tn is equal to 0, right? That is Tn approaches to 0, right? So therefore for epsilon greater than 0 there exists m such that Tn is less than epsilon by 2 for all m greater than n greater than equal to m, right? But in place of this you can also write epsilon. So epsilon, ठीक है, इसकी जगह आप सिंपल epsilon लिख सकते हो, but I'm writing epsilon by 2 for a reason, okay. So this reason I'll be telling you later, okay. Again, okay, again, ठीक है, ये किसको कन्वर्ज कर रही है, जीरो को कन्वर्ज कर रही है। जीरो को कन्वर्ज करने का अगर कोई सीक्वेंस, इट मीन्स टी एन इज कन्वर्जेंट। अगर टी एन कन्वर्जेंट है तो ये बाउंडेड होगी, हमने थ्योरम पढ़ी हुई है पहले की, ओके। सो देयरफॉर वी कैन राइट देयरफॉर टी एन इज लेस देन इक्वल टू के, ओके, सम के फॉर ऑल एन because this is bounded sequence, okay. You can write this here, okay, because Tn is convergent, thus bounded, okay. So it would be bounded by some upper bound and some lower bound, right? So now हमें show क्या करना है, we have to show that देखो हमने इक्वेशन नंबर 1 में क्या प्रूव कर लिया, 1 सेकेंड, you just see we have proved in equation number 1 that xn is equal to this, okay. So now take this mod, okay, up to so on plus n divided by n, okay. So it is equal to, it could be written equal to t1 plus t2 plus up to so on, बीच में कहीं m भी आएगा because m is lesser than n, okay. So tm plus 1 up to so on plus tn divided by n, okay. Further, so this is equal to t1 plus t2, ओके, लेस देन इक्वल टू कर देता हूँ इसको, सिंपली पहले आप इक्वल राइट करो, ओके. सो इट इज इक्वल टू equal to up to so on, okay, t1 plus t2, ये I'm going to separate this and this, okay, divided by n plus tm plus 1 up to so on tn divided by n, right? So now I can use modulus inequality t1 plus t2 plus up to so on plus tm divided by n plus tm plus 1 up to so on tn divided by n, right? So now you can see further, if you can use a modulus inequality further, right? So you can write it as t1 plus t2 up to so on tm, okay, it is m, divided by n plus tm plus 1 plus tm plus 2 up to so on plus tn divided by n, okay. So जब भी n किससे ग्रेटर होगा, m से ग्रेटर होगा या इक्वल टू m होगा, ओके, फॉर दैट नंबर यू आर गोइंग टू राइट, ओके, फॉर ग्रेटर देन m यू आर गोइंग टू राइट, सो हम ये वाला m यहाँ पे भी लिख सकते हैं ना, कोई प्रॉब्लम नहीं है उसमें भी, ओके, बट we have already taken this on the left hand side, so you just carry on with this only, okay. So now we have seen that tn is less than equal to k for all n. Also we saw tn is less than epsilon by 2 for all n greater than equal to m, these two things, okay. So we can write here this is lesser than, okay, ये सारी टर्म किससे छोटी हैं, ये होगी, these are lesser than what, k, okay. So total number of term here is m, okay. So mk divided by n, okay, plus ये वाली सारी टर्म, ठीक है, जब m ग्रेटर हो जाता है किस, n ग्रेटर हो जाता है किससे, m से, तो किससे छोटी हो रही है फिर, एप्सिलॉन बाय 2 से. सो वी आर गोइंग टू राइट एप्सिलॉन, ठीक है, ये टोटल नंबर ऑफ टर्म्स कितना है, n minus m plus 1 plus 1, okay. So this cancel, so we are having total number of terms n minus m epsilon by 2 divided by n, right? So this is the this is the thing we get after the simplification, okay, using, okay, you can write using 2 and 3, right? So nextly this, okay, so simplifying this we get epsilon by 2, okay, n से n cancel हो जाएगा, minus me by 2 n, okay. So अगर हम माइनस वाली टर्म छोड़ देते हैं, it would be more greater, okay, और ज़्यादा ग्रेटर हो जाएगी, तो we will be having mn plus epsilon by 2, okay. So we know as n goes to infinity, mk divided by n also goes to 0, right? So therefore t1 plus t2 up to so on tn divided by n is less than epsilon by 2, okay. सो वन से आप शुरू में क्या कीजिए, जहाँ पे आपने एप्सिलॉन बाय 2 लिखा था वहाँ पे सिंपल एप्सिलॉन लिख दीजिए, सो इट वुड बी लेसर देन एप्सिलॉन, ओके, एज इट गोज, सो इट गोज एज n tends to infinity, so this term is also epsilon is random, okay, it could be very small. If this is very small, this means t1 plus t2 up to so on divided by n is equal to, also this limit is also 0. So okay, so what is tn? Tn is what? Tn is nothing but an plus l, right? So if you substitute back this value, so we get a1 plus l up to so on, okay, इस तरह से a2 plus l up to so on an plus l divided by n, okay, it is equal to 0. Oh, I'm sorry, Tn is equal to minus L. Okay, an minus L, so it is minus here, minus. Okay, so in this way we get limit n tending to infinity an plus a2 up to so on divided by n, okay, minus L is equal to 0. Okay, so taking this limit to the other side, we get this is equal to L. So hence in this way we have proved the theorem, right? So this is it for today, right? Rest of the things will be done tomorrow. Thank you.